Alright guys, so this is our Flip the Classroom lesson on building functions from functions. And when we're talking about building functions from functions, basically what we're doing is taking an initial set of functions and creating new functions by combining the equations that define the initial functions. When we're combining functions with operations, that means that we're going to be combining the equations that define those functions with addition, subtraction, multiplication, and division to get our new functions. Right here we've got an initial set of functions, s of x, h of x, and d of x. And what we want to do is first define the domain of each of the initial functions. Because when we combine our functions, we're going to use those domains, or restrictions on those original domains, to come up with the domains for our new functions. So right here, s of x is x plus 2, right? And we can see that with this x plus 2, we're not violating either of our two restrictions, 0 in the denominator or negative under an even radical. So right here, because there's no way to do that with this equation, we can say that our domain for s of x is all real numbers from negative infinity to positive infinity. Right? With our h of x, we've got 1 over x minus 2. We know that we can't have any x value that will give us 0 in the denominator. And so right here, for our x minus 2, an x value of 2 would give us 0 in the denominator. So we would take out the x value of 2 from our potential inputs and get a domain of negative infinity to 2 union with 2 to positive infinity. For our d of x, we've got the square root of x, and we know that we can't have any x value that will give us a negative under an even radical. So right here, that means that x cannot be less than 0, and our domain will be from 0 to positive infinity, including 0. So here we have our initial functions and their domains. And what we're going to do now is talk about combining some of these initial functions to get new functions. Right here, when we combine our initial functions with operations, basically what we're doing is just combining the two equations with whatever given operation we're asked to combine the functions with. So right here, if we've got h plus d of x, that's adding the equation h of x plus the equation d of x. And right here, what we're going to get then is the addition of the equation defining h of x, which is 1 over x minus 2. And we're going to add that to the equation that defines d of x, which is the square root of x. Now, right here, I put up parentheses, and I think that that is a good habit to get into. In this particular case, h plus d of x, it really doesn't make a difference. We don't really need parentheses when we're combining our two functions, because if we took down parentheses, we'd have the exact same expression. But if we look at something like, let's say, d of x, or let's say d minus s of x, this would be the equation d of x minus the equation s of x, which basically means the function is going to be taking the values of s of x and subtracting them for the corresponding values of d of x. So right here, the equations for d of x come from that square root of x, and the equations for, or the values for s of x come from that x plus 2. So right here, x plus 2 gives us the values of s of x for any specific x value, and we'd subtract those from the square root of x. Now right here, simplifying means that we would distribute the negative through those parentheses. So right here, we would have our d minus s of x equal to the square root of x minus 2, right? And that's, of course, a lot different from if we just combine the two expressions without parentheses, which would be the square root of x minus x plus 2. So right here, this is not d minus s of x. And that's an important thing to recognize here. So even though taking down the parentheses in our expression for h of x plus d of x doesn't really make any difference. It's an important habit to get into because sometimes you're going to run into scenarios that when you want to simplify that combination of expressions, you get a different equation if you didn't have parentheses. So right here, what we're going to do now is go ahead and define the domain for our new function. And the way we're going to do this is we are going to determine the restrictions from each of our parentheses and then see if we get any restrictions from the composition or the addition of these two equations. So right here, our first restriction is that for our h of x, x cannot equal 2. And for our square root of x, x cannot be less than 0. And so right here, defining our domain, we're going to throw out all values less than 0 and the x value 2, and we're going to get the domain from 0 to 2, union with 2 to positive infinity. And that is the domain of our new function, x plus d of x. Now right here, what we can do is simplify this equation by just taking down our parentheses. It doesn't make a huge difference, but it's a little easier to look at. So right here we'd say h plus d of x would be 1 over x minus 2, and then right here plus the square root of x. And that would be our new function with the given domain right here. Now, obviously simplifying doesn't change the domain at all. But what we're going to see in our next example is a new function that simplifying is going to affect the domain, or is going to affect is going to look like it's affecting the domain. But remember, when we're defining the domain for our combination of functions, we always want to evaluate the domain from the instant we bring those two functions together. So right here, just looking at this, we've got s divided by h of x, and that of course means the equation s of x divided by the equation h of x, which would give us x plus 2 divided by 1 over x minus 2. Now right here, we're going to evaluate the domain restrictions from each of our parentheses and then identify any additional restrictions that would come from bringing these two equations together with division. So initially right here we can say that because of this 1 over x minus 2 in the denominator, we can't have the x value of 2. And so we're going to throw that x value out of our domain. Now right here we're also going to say that 1 over x minus 2 can also not equal 0. But what we can see here is that there is no x value that can make 1 over x minus 2 equal to 0. Right here, if we plugged in 0, we'd of course have negative 1/2. If we plugged in 2, we'd already be defined, and we've already thrown out the x value right there of 2 that would give us 0 in the denominator there. So right here, our domain for our combination here would be from negative infinity to 2 union with 2 to positive infinity. Now that's the domain of our new function. Now what we're going to see right here is that the simplification of our expression right here is going to mean that it looks like this restriction is going to go away. So right here, looking at s of x divided by h of x, we've got x plus 2 divided by 1 over x minus 2. And when we're dividing by a fraction, that means that we multiply by the reciprocal. So we've got x plus 2 times right here x minus 2 over 1, or just x minus 2. And right here, when we multiply these two binomials together, we get x squared minus 4. Now, right here for this equation, we no longer have the restriction x cannot equal 2. But if we think about it, this new function, right, h divided by h of x is really the function values for s of x divided by the function values for h of x. So right here, h of x is not defined for the x value of 2, so it cannot be a part of the domain. Now what we're seeing here is that if we looked at the graph of our s divided by h of x, what we would get is the graph of x squared minus 4, right, without an ordered pair for the x value of 2, right? And we can sort of take a look at that on the calculator. So right here, what we're going to do is take out our calculator. So right here, taking out our calculator, we're going to type our h divided by s of x, not simplified, into y1. And we'll type in our simplified equation, x squared minus 4, into y2. So y1 will appear in blue and y2 will appear in red. Now right here, when we graph these two guys, what we're going to see is the graph of y1, right? That's our s divided by h of x graph first in blue. We won't see that ordered pair missing, but we'll see in the table later. And what we're going to see is the graph of x squared minus 4 go right over that graph of s divided by h of x. So right here, looking at the graph, there's that graph of the original unsimplified equation. And there is the graph of the simplified equation, right? Now right here, when we look at the table, what we can see is that, of course, we're going to come up with all the same function values for the input x values, except for at x equals 2. And at x equals 2, what we're seeing is an error for the y1, that unsimplified version, which is the equation s divided by h of x, and, of course, the output of 0 for the equation x squared minus 4. So really what we get here when we simplify is an easier way to look at the graph of the function, but of course we have to respect the original domain, or the domain of the function in the unsimplified form. So right here what we would say is if we had this equation s divided by h of x, we would represent it with the simplified equation x squared minus 4, but we would have to say for the restricted domain of negative infinity to 2 union with 2 to positive infinity, right? So that's something that we want to sort of take into consider when we're working through these. Again, right here, it's pretty simple. When we're combining functions with operations to create new functions, really all we're doing is basically taking the whatever operation that we're combining with and combining the equations that define the functions with that operation, right? We define the domain. At the moment that we bring those two functions together, we first define the domain restrictions for each equation individually, right? And then what we're going to do is see if there are any restrictions that come from the combination of those two equations with the given operation. And then, of course, we'll have our domain. And then we can simplify that equation, taking down the parentheses and basically canceling anything out, because we'll know the restricted domain we're going to get for the graph. All right, guys, so we're going to let you try some building of functions from functions with operations on your own. We've got an initial set of functions here, f of x, k of x, and g of x. You guys are going to go through and determine the domain for each of these functions, and then you're going to create new functions by composing these functions with the given operation. So right here we've got the sum of functions. We're going to be adding functions, difference of functions, subtracting functions, product of functions, multiplying functions, quotient of functions, that's the division of functions, and then right here the squaring of functions just basically means multiplying a function by itself. So right here we've got g times g of x, and that's literally going to be g of x times g of x, right? Now right here, when we're combining these functions, we first want to remember that we're going to be taking the equations that define these functions and combining them with the given operation. And as soon as we do that, we want to determine the domain. So when we're determining the domain, we're going to determine any restrictions that come from the two functions individually. And then we want to think about any restrictions that could come about from the combining of the two functions with the given operation. And a lot of that's going to be intuitive. I mean, it sounds more complicated than it is. You'll see with the first couple of examples that really when you look at the function itself, the domain is going to be pretty self-evident. But after you determine the domain, what I want you guys to do is simplify the equation. Sometimes that's just going to mean taking down the parentheses that we used to combine the two functions initially. And that's it. So right here, these are we're starting out with some pretty simple examples. And towards the end of this page, we've got some that you have to think a little bit more about. Right here, what I want you guys to do is to just go ahead and pause the video and give these a shot on your own. And we will come back in a second and look at the answers together. All right, guys, so for the domains of our initial functions, we've got no restrictions on f of x, right? No way to have 0 in the denominator or a negative under an even radical. So the domain is going to be from negative infinity to positive infinity. For our k of x, we have 1 over 2x. So right here, we cannot have the x value of 0 because it's going to give us a 0 in the denominator there. So we exclude that from the domain, and we have negative infinity to 0, union with 0 to positive infinity. And of course, g of x right here is the square root of x plus 1, and that means that we cannot have any x value less than negative 1 because it's going to make that expression underneath that even radical negative, and we can't have a negative under an even radical. So our domain is from and including negative 1 to positive infinity. Okay, so right here, let's look at first summing functions. So f plus g of x is, of course, the equation defining f of x plus the equation defining g of x. And right here, we've got that x squared plus 4 for our f of x, and then plus our square root of x plus 1 for our g of x. Right here, f of x is not going to give us any restrictions, but our g of x expression, of course, is saying that we cannot have any x value less than negative 1. And of course, the composition of, or the sum of these two equations isn't going to create any new restrictions. And that's most of the time going to be true, but we're going to run into some cases later on where bringing two equations together with some operation is going to create some additional restrictions. So right here, with our one restriction of x not being less than negative 1, we can say our domain is from and including negative 1 to positive infinity. And then simplifying this is basically just going to be taking down the parentheses. So not a whole lot of work to simplify either. So right here we've got f plus g of x is x squared plus 4 plus the square root of x plus 1. Okay, so right here for our difference of functions, we've got f minus k of x, which is the equation defining f of x minus the equation defining k of x. Again, right here, looking at our parentheses first, no restrictions for our f of x, and k of x, we know, cannot have any x value, or cannot have the x value specifically of 0, right? Because that's going to give us 0 in the denominator. So right here, the subtraction of these two equations is not going to create any new restrictions. And therefore, with our one restriction, we can say our domain is going to be negative infinity to 0, union with 0 to positive infinity. And then again, taking down the parentheses is going to be what simplifying our new function is going to entail, right? As soon as we take down the parentheses, we've got x squared plus 4 minus 1 over 2x. We could combine these terms and get one fraction, but this is a simplified enough form for us for sure. It's easy enough to evaluate. We can sort of talk about what the graph of that would be pretty easily, so we don't want to do any more manipulation to that equation. All right, so for our product of functions, we've got g times k of x, which is the equation for g of x times the equation for k of x. So right here, we are going to end up with restrictions for each of our parentheses here. For our square root, we know x cannot be less than negative 1. And for our 1 over 2x, we know x cannot equal 0. So we've got those two restrictions. The multiplication of these two equations is not going to create any new restrictions. So with our two restrictions, we can determine a domain that goes from negative 1 to 0, union with 0 to positive infinity, including negative 1, but of course not including 0. And right here, our g times k of x, the simplified form of this equation, would basically just be that square root of x plus 1 multiplied into the numerator, right? So that would be sort of the condensed version of the combination of those two equations with multiplication. Okay, so for our quotient of functions, we've got f of x divided by g of x, which is the equation for f of x divided by the equation for g of x. And right here, we are going to see a new restriction come from this division. So right here, our f of x, again, is not going to have any restrictions. We know that our g of x is going to have the restriction that x cannot be less than -1. And because that square root is in the denominator, we also can't have the square root of x plus 1 be equal to 0. So that means that x cannot equal -1, right? So now our domain is going to include both of these restrictions, and it's going to be from and not including -1 to positive infinity, right? So that's the domain for the division of these two functions. And a simplified version of this would, of course, just be taking down the parentheses, so there's not too much work there either. There will become some problems where we have to do more simplifying work, but on this first page, I want you guys to sort of get a hang of getting those new domains and determining the domains for these functions that we're building from operations. So right here, the simplified version is just x squared plus 4 divided by the square root of x plus 1, which of course is just taking down the parentheses. Now, right here, we do have a function, a new function that we're getting from squaring of functions that is going to have some simplification, and that simplification is going to look like it takes away some restrictions. But again, we want to note that we get the restrictions for our domain from that point where we bring those two functions together with whatever operation we're using. So right here we've got g times g of x, which is the equation for g of x, times the equation for g of x again. And so right here we've got the square root of x plus 1 times the square root of x plus 1. And of course both of these parentheses have the restriction that x cannot be less than -1, right? So right here we don't get any new restrictions that comes from the multiplication of those two parentheses. So with our one restriction, we can determine that the domain is going to be from and including -1 to positive infinity. But what happens when we simplify, take all this away, what happens when we simplify is that we've got the square root of x plus 1 times the square root of x plus 1, which is the square root of x plus 1 squared, and the square root cancel out. And so right here what we end up with for the simplified version of our new function is just x plus 1, right? So what we would say is that this function, g times g of x, is x plus 1 on the given domain. Now, of course, x plus 1 as a function on its own is a linear function that has a domain of positive infinity to negative infinity. But because this equation came from the multiplication of our two square roots right here, remember that what we're saying is that we're multiplying the function values for g of x times the function values for g of x. And since g of x is undefined when x is less than -1, we're going to be getting the function as this x plus 1 on the domain from -1 to positive infinity. Now, if you were to graph in your calculator the square root of x plus 1 times the square root of x plus 1, or even the square root of x plus 1 squared, what you would see is this linear function up into -1. So right here, we would see from -1, the graph of that linear function on the domain that goes from -1 to positive infinity, but we wouldn't get any function values behind -1, right? Even though the linear function on its own, if you graphed y equals x plus 1, you would have the entire line. This g times g of x is just x plus 1 on the domain -1 to positive infinity. I think we've nailed that home. So right here, this is building functions from functions with operations. In our next video, we're going to talk about building functions from functions with composition. And we will see you guys in the next